Welcome to this movie which deals with thermodynamics. My name is Jos Dyson and I teach advanced statistical mechanics in the master program on applied physics at the Delft University of Technology. And I've made this movie in order to review quickly what the students should know about thermodynamics, because one of the main aims of statistical mechanics is to provide, say, based on the microscopic details of the interactions between the particles making up the material surrounding us, like the air and the objects that we see. So the aim is to explain the macroscopic behavior which is described by the laws of thermodynamics from the microscopic principles, and therefore it's useful first to refresh the knowledge of thermodynamics a little bit again. And that's what I've tried in this movie, and I hope that it's useful for anyone in need of a review on this topic, which in fact is quite difficult, I think. We start by considering a system which is confined to a box. The box has a rigid shape, a fixed shape, and the volume of the box is V. And in this volume we put n particles which interact and which move around, so they have an energy which we call E. And now we are going to take a second box which is identical to the first one. So I just copy and paste this box, which represents obviously also a volume V, a particle number n, same number of particles in the box, and therefore they have the same energy because the particles are all the same. Now suppose that we move those two boxes together. So we get a box which has twice the size of the original boxes. So initially we had a situation like this. There was a wall separating the two boxes. And now we remove that wall, and if the particles only interact at in a short range, then the energy obviously is the energy of the left box plus the energy of the right box, which is 2E. The volume obviously has doubled too, and also the number of particles has doubled. So that means that if I take a box which is twice as big as the original box but otherwise the same, then these quantities all double, and quantities which have this property are called extensive variables. So extensive variables scale with the system size. If I make the system twice as big, all these variables also double in size. Now, one of the most important statements made in statistical mechanics is that there exists a quantity called the entropy, which is extensive. So if I double the system size, also the entropy doubles. And it's also concave. So entropy is denoted by the letter S. So S is the entropy, which is a function of some variables of the system, and in this case it's a function of the extensive variables E, N, and V. And as a function of these variables, the S is concave, which means that its shape is like a dome. So in one dimension, if I take one of these variables, then S as a function of those variables always looks like this, and it never looks like this. Concave is a mathematical property. In fact, we can formulate it a little bit more accurately as I've done before. So for a function f which is concave, it has this shape, and suppose that we approximate that function by the line tangent to the curve at the point x1, then the value of f at some other point x2 minus f at the point x1 must always be smaller than df dx1 times x2 minus x1. So what this says is that this tangent line is always higher than the function close to the value x1 and also far from the value x1. And for the entropy, it holds that it's a concave function of the energy, concave function of the number of particles, and it's a concave function of the volume. Now, those are only two properties of this new quantity, which is called entropy. It's extensive and it's concave, and there is also a third property and a fourth one. The third property says that S should be a monotonically increasing function of the energy, which means that the derivative of the S with respect to the energy, and we suppose that N and V are kept constant, that should always be greater than 0. And furthermore, but this is not a property of the entropy, but it's just a definition, ds dE for constant NV, which is always a positive quantity, as we have seen, we call that 1 over T, where T is the temperature. The fourth property is that in a closed system which is left on its own, the entropy can only increase, so it cannot decrease. And what happens when the entropy reaches its maximum? Then the system is in equilibrium. So in the equilibrium, the entropy assumes its maximum value. Now that we have all these properties of the entropy, we can analyze the derivatives of the entropy with respect to its variables. And we do that using just physics. We have a thermally conducting fixed wall which separates two volumes, two subvolumes. One volume has a number of particles N1, a volume V1 and an energy E1. The other has E2, N2 and V2, and the entire system is insulated, so this thick wall is insulating, which means that there is no energy leaking out, there is no work done on the system, and from that we infer that the total energy E1 plus E2 must be fixed. And so if we take the derivative with respect to E1 of a quantity like the entropy, we see that this is minus dE dE2. And now we use the fact that the entropy is at its maximum. Well, in fact, there is only one quantity that we can vary in this case, which is the energy. The number of particles is fixed in the left and right compartment. The volumes are fixed because the wall separating them is fixed. But there is energy which can leak through this wall from left to right or from right to left. So the only quantity that we can change, say, is the energy in compartment 1. Due to the fact that the total energy is fixed, once we know the energy in compartment 1, we also know the energy in compartment 2, so that's not a separate degree of freedom. And so what we can say is that if S reaches its maximum, then we should have ds dE1 must be 0. And we can write that as ds1 plus S2 taking derivative with respect to E1, and obviously I suppose when I take this partial derivative that all the N1s, the V1s, etc., they are all fixed. It's only the energy which can vary. And we can write this as ds1 dE1 plus ds2 dE1. But now we use this rule which says that this is equal to S1 SE1 minus ds2 dE2. And so this should be 0, which means that the ds1 dE1 is equal to ds2 dE2, and obviously we take N1 and V1 fixed. We also keep N2 and V2 fixed. And now we note that previously we had defined ds dE as 1 over the temperature. So we can write this also as 1 over T1 should be equal to 1 over T2. In other words, what we find is that T1 is T2. Not surprising if I have a thermally conducting wall separating the two compartments. If we wait long enough so that the system is in equilibrium, the temperature on the left-hand side will be equal to the temperature on the right-hand side. Now we play a similar game for a different system, which has a thermally conducting wall, just like before, but now the wall can move. So the wall can move from left to right, which means that we can vary not only the energy can move through the wall, but we can also change the volumes V1 and V2. And therefore, in addition to what we had before, the derivatives of the entropy with respect to energy, we consider now the derivatives of the entropies with respect to the volume. And so we get for the total entropy, which is S1, S2, we take the derivative with respect to V1. Because the two volumes add up to a fixed number, only the V1 can be varied, and we have ddV1 is ddV minus ddV2, just as before with the energy. And therefore we can write this as ds1v1 minus ds2v2, and that must be 0, so the ds dV on the left hand side must be equal to ds dV on the right hand side. Now we know that the temperatures in equilibrium are equal. We have just seen that because the two systems can exchange energy. And if the wall comes to a rest, that can only happen when the pressure on the left-hand side of the wall is equal to the pressure of the right-hand side. So we should have something like a pressure on the left-hand side being equal to the pressure on the right-hand side. And now I have put a P over T. Well, why did I do that? Well, previously we have seen that ds dE at constant n and v, that's 1 over t. So that means that the dimension of s over e is the dimension of 1 over t. Now I don't have the derivative of s with respect to e, but I have the derivative with respect to v. So to the dimension of this 1 over t, I must add a dimension of, well, I miss the e in the denominator, but instead I get a v, and this is the same as the dimension of pressure. So already the dimensional arguments tell me that I should add a 1 over t here. So ds dV, that's the bottom line, evaluated at constant n and e, is equal to P over T. Finally, we consider a system where the wall is again fixed, so there is no freedom in the volumes, but now we make a little hole in the walls, and so particles can move from left to right. So the n1 is an extra variable, and I can play the same game as before. And now we obtain the condition that ds and ds1, dn1 is equal to ds2, dn2. And if the systems can exchange particles, that will stop once the chemical potentials on the left and right hand side are the same. So we have a new quantity. You could view this as the definition of chemical potential, in which we have included this 1 over t, which fixes the dimension of mu to be in energy. Obviously, because the wall is also conducting, the energies are the same on the left and right hand side, and we find that the temperature on the left and right hand side are the same. So what have we found? We have an entropy which we wrote as a function of the energy, the volume and the number of particles. Then we took the derivatives. So this guy is the STE. That's the temperature. And this guy is the S. It's T times the SdV, because the SdV was P over T. And this is T times the SdN. That's the mu, the chemical potential. And temperature, pressure and chemical potential, they don't scale with the system volume. So if I double the system size, these guys double in value. But obviously, if I make a room twice as big, then the temperature doesn't add up. It doesn't become twice as big. And the same holds for the pressure and the chemical potential. So these are intensive variables. They do not scale. Not scale. With the system size. Now we focus on the quantity energy. We want to change the energy of a system, and we can do that in two ways. The first one is the way when you cook, for example, when you boil water on in a water kettle or on the gas, then you add heat, and so the change in energy can be due to adding heat, and the heat that you add to the system is given the symbol Q. And another way to change the energy of a system is by doing work on it. We can, for example, if we have a gas in a balloon, we can compress the balloon or we can stretch it. And so in addition, we have work. Work is usually denoted as W, so we have dW. But now it happens that depending on the steps that we take to change the energy, the dq and the dw do not always have the same value, even if the initial and final state of our system are the same. So the energy change for an initial and the final state, the difference between the energy in the initial and in the final state, that's always the same. But the amount of heat that we had to add to the system and the amount of work that we had to do to the system may depend on, for example, first we heat it up and then we let the system do work, or first we do work on the system or let the system do work and then we add or extract heat. Then these quantities are both different, although their difference is always the same. Well, differentials that depend on the way we proceed, they are usually called non-exact differentials, and I indicate that with a dash through the D. So these are non-exact. But the energy is an exact differential, which means that it doesn't matter how I go from state 1 to state 2, the energy difference between state 1 and state 2 is always the same. This first quantity is the heat that is added to or extracted from the system. That whether it's added or extracted influences the sign of this guy. And this is the work. And this statement, which is given here, that's known as the first law of thermodynamics. In this picture you see the two ways in which we can change the energy. We can either heat the system with a small flame, or we can have a piston which is moving from left to right. There is a force associated with that, and so we have a work which is force times displacement, and it's not difficult to see that the work, let me put that in black, is given by the pressure times the change in volume of the system. Recall that the volume change is the surface area of the piston times its displacement, and the force is the pressure times the displacement, and from that it's easy to find this relation. Now I should say something about the signs. So dq, that is the heat flow into the system. And dW is the work done by the system. In fact, this fixes the sign of the two quantities, the sign with which they appear in the first law, and sometimes people use different definitions. For example, for dW they use the work done on the system, and then this sign, the minus sign, switches into a plus sign, so it's just a convention. Finally, we could of course also change the number of particles in the system by putting a hole in here and then feed extra particles into that volume. And in that case there is an extra contribution to the work. So more generally we can write that dW is pdV minus mu dn. Where mu is the chemical potential. When we have a thermodynamic system that we leave on its own, it may change. For example, if it was not in equilibrium and it moves towards equilibrium, there is a change. And we can also perform a change on the system. And in all these situations in which the system changes, that's denoted by the term process. It's a thermodynamic process when we change it, or when the system changes by itself. And there are different types of processes that we want to distinguish. The first type of process that we want to distinguish is the quasi-static process. If we have a piston which closes off a system, like we have seen before, then we can move the piston so slowly that the gas is always very close to equilibrium. That's an example of a quasi-static process. The other example is that we have an escape or an addition of particles which is so slow that the system always is in equilibrium. So those processes are called quasi-static. The second type of processes that we distinguish are reversible processes, and those are processes for which the heat added to the system is the only cause of a change in the entropy through the relation dq is TdS. The third type of processes that we distinguish are spontaneous processes in which the heat is smaller or equal than TdS. In fact, the second law of thermodynamics tells us that TdS is always larger or equal than dq. So for reversible processes we have the equality sign. For spontaneous processes, in fact, we have the strict greater than sign. Finally, there are adiabatic processes, and they are characterized by dq is 0. In other words, there's no heat flowing into or out of the system. So now we consider a quasi-static process in which there is no work being done by or on the system. So dW is 0. And this is an example of this is when you have a pressure cooker and you heat up the liquid in it very slowly. Let us see what happens to the entropy in that case. So we look at the change in entropy during a quasi-static process, and we take the infinitesimal change. So the ds is the S after we have added the heat, so that was S depending on E, plus we have added a small amount of heat, And I neglect now the N and the V because they are kept constant. And from this we subtract the S that we had before the heating process. And if we use a Taylor expansion because the dq is small, we can write this as dq times ds dE evaluated at constant volume and number of particles. We know that this quantity is 1 over T, and so we have dq over T. So in a quasi-static process, we can write that the change in entropy is simply given by dq over T. So we find that dq is TdS, which means that this process is reversible. So if we have a quasi-static process where there is no work done by or on the system, we find that it's automatically a reversible process. In general, for spontaneous processes, we find TdS is greater than dq, and that statement is in fact the second law of thermodynamics. Then we consider a reversible process in which the total energy doesn't change. So the fact that the process is reversible enables us to write dq as TdS. The dW is minus pdV. And what we find from this is that ds dV is P over T. And that is precisely what we found before when we were analyzing a system with a movable wall. Here we found also that ds dV is P over T. So what we can conclude is that in general the change in the energy for a reversible process is given as TdS minus pdV plus mu dN. Now we are going to consider two different systems. They look identical now. There is a red fixed piston which just closes off the system, and there is a green piston, and that piston can move, and on the left hand side it will move very slowly up. So this is a quasi-static process because the piston moves only very slowly. And now these particles here are bouncing off this piston, and because the piston is moving up, they will on average come back at a slower velocity. With a slower velocity, they all will come back with a slower velocity than with which they hit the piston. So that means that their kinetic energy is going down, and that implies that the temperature is going down too. So the temperature decreases due to work done by the piston. We assume that the black walls are insulating, so the dq is taken 0 here. Now on the right hand side, what we do is we have also a piston, or it's a wall which closes off the lower compartment. There are similar amounts of gas present in the lower compartment, but now we pull this piston away very quickly to the right. And from that moment on, all these atoms can move in the entire volume. And if we assume that they are ideal, that they form an ideal gas, then of course they do not change their velocity at all. The average velocity will just remain the same, and so T remains constant. We know obviously that the pressure will go down because the gas will occupy a larger volume. So in this case, then also the entropy will change. So this is a quasi-static process. This is an example of a sudden process. So that means that the particles do not have the opportunity to interact with the piston and thereby change their velocity. And for the sudden process, the work done by the piston, because it's moved sideways, and the pressure, of course, the force could only pull it up or down. Therefore, the work done is 0. Okay, there's no work being done. But on the other hand, because the particles have now a larger volume which they occupy, the delta S will be larger than 0. And so, because everything is also adiabatic, so we have delta Q being 0, we see that this is a nice example of delta S being larger in general than delta Q over T. Now we're going to consider two systems that are connected together thermally, so there can be a heat flow from one system to the other. I could call this delta Q, or I can call it delta E. It's the same because there's no work being done. The wall is considered to be fixed. So let us see what happens to the entropy. Now we assume that the entropy versus the energy for system 1 and system 2 follow these curves. Now you see clearly that if the system 1 is somewhere at this energy, the slope of this curve is larger than the slope of this curve. But the slope of this curve, that's ds dE, it's 1 over T. So the larger slope means a lower temperature. So this is the cold system, and it's cold because the ds dE is high here. Here the slope is low, and therefore this is a hot system. And now we assume that so this is the cold system, this is the hot system, and we assume that the heat is flowing from cold to hot. So that there is a positive amount of heat flowing from cold to hot, which means obviously that the cold system would lose energy, delta Q, and the hot system would gain an energy, delta Q, and these are the same in size, because what is lost by system 1 will be gained by system 2. Then if we consider the delta S of the cold system, delta SC, and we add to that the change in entropy of the hot system, then we clearly see that this is a large negative quantity because the entropy goes down quite a lot, and this is a small positive quantity, and therefore we see that this is smaller than 0. But that's the same as the total entropy change. And in the beginning we have said that if we leave a system on its own, like this one, the entropy can only increase. So what we see here is impossible. And therefore we see that the property of the entropy, namely that it's always trying to reach its maximum, that forbids heat to flow from a cold to a hot system. So heat always flows from a hot to a cold system, and the reason behind this, or the explanation that we have found now, is based in the notion that the entropy also always goes up. And this is called often the second law of thermodynamics, a certain formulation of the second law of thermodynamics, and that is that heat can never flow from a cold to a hot system. So delta S, the heat flows from hot to cold. And that's a particular formulation of the second law. Now we consider an engine which uses a hot reservoir and a cold environment in order to do some work. So we have here the hot reservoir, here is the cold reservoir, and we assume that there are no spontaneous processes and that the entire system, so the cold and hot reservoir together, that they are isolated from the environment, so we have no heat flow, and therefore the delta S should be 0. From this picture we first immediately can see a balance equation, because the heat which is leaving the hot reservoir will partly flow into the cold one, that's the QC, but it will partly be used for work, and therefore we have QH is QC plus W. And what we are interested is in how much work can we extract from the system as a fraction, viewed as a fraction of the heat which is flowing out of the hot system. So that's called the efficiency, and it's W, it's the useful work divided by the heat that we lose from the hot system. And we assume that also inside there are no spontaneous processes taking place, so we can always write delta Q hot as T times the change in the entropy of the hot system, but we should take a minus sign here, because if the entropy typically the QH is a positive quantity, and that's heat which leaves the hot system, and therefore we have a loss of entropy. Usually we define the heat as the heat which flows into the system, and because here it flows out of the system we have the minus sign. Then for the cold system we have a similar equation, but then with a plus sign, because the heat is flowing into the cold system. So we have delta T times, and this is T hot, and here we have T cold times delta SC. And now if the system as a whole is really well insulated, but still the hot reservoir is extremely big, the cold reservoir is extremely big, so they keep their temperatures. The temperatures do not change, but the two together are well insulated. Then we have that delta QH, delta S, which is delta SH plus delta SC, that should be 0 for a reversible process, and that immediately leads to the conclusion that minus QH divided by TH plus QC divided by TC equals 0. So we can conclude that QH over TH is equal to QC over TC. Now let's have a look at this efficiency. We call it the Carnot efficiency. For a reversible process we have the Carnot efficiency, and we can write that as W in the numerator, and that's QH minus QC. And we must divide that by QH, which means that we have 1 minus QC over QH, and we see immediately that that is TC over TH. And so this is the Carnot efficiency. And a natural question is then, what would spontaneous processes do to this Carnot efficiency? Now we consider what happens if the entropy would increase. If delta S is greater than 0, we write this delta S now as the change in the entropy of the hot system, and that of the cold system, where the hot system obviously has a minus sign because the heat flow is out of the hot system. And then we find that QC over TC is greater than QH over TH. In other words, QC over QH is larger than TC over TH. Now let us look at the efficiency, which was here. We see that it has the form 1 minus QC over QH. That's the actual efficiency. And because this quantity now is larger than TC over TH, and it occurs with a minus sign, we see that this is smaller. It's strictly smaller. If we have here delta S being strictly larger than 0, it's smaller than 1 minus TC over TH, which is the Carnot efficiency. So we put a C there in order to indicate that it's the Carnot efficiency. So what we have seen is that there is a maximum to the efficiency of such a machine, and that maximum efficiency depends on the temperatures of the cooled and hot reservoir. In real life, there will always be a small increase of entropy, and that increase of entropy will reduce the efficiency with respect to the Carnot efficiency. At the start of this movie, we have introduced the entropy as a function of the energy and the number of particles and the volume. Now here I've drawn the entropy as a function of the energy and some other variables, which could be the particle number or volume. That depends on the type of system I'm looking at. But this is just a representative picture of the entropy. What can we say about this picture? Well, first of all, we see that the entropy, let me write it up here, EVN or ENV, whatever you like. It has a dome shape. It is a concave function. And so it will have a maximum, for example, as a function of x. It will not have a maximum as a function of E, because we have seen that ds dE, that's the temperature, or 1 over the temperature, that should always be positive. So as a function of E, S should not only be concave, but it should also be monotonically increasing. And the blue line represents all the equilibrium points. Those are the points for which S has reached its maximum as a function of x, and if we have then a fixed amount of energy, then the point on the blue line that we cross, that is where the equilibrium situation is. And what we want to do now is we want to invert this function in order to obtain a function of representing the energy as a function of entropy, volume and particle number. And we can do that because the entropy is a monotonically increasing function of the energy. So this is our new function, and in order to see its behavior, so let us in fact now read this as our variable x. So let us consider the function e as a function of x for fixed s. Well, if we fix s here, we have a horizontal plane and it cuts the surface at the green line. So the green line corresponds to fixed s. And we can read off here what the energy then does. And we see that at the equilibrium point, the energy has reached its minimum as a function of x. So E definitely has a minimum, and that means it's no longer a concave function of x as the entropy was, but E is a convex function. So now we see that it's inverse of a dome. Also, as a function of s, it turns out that a concave function now turns into a convex function. So this function is convex, and the energy as a minimum as a function of x, but it's an increasing function still of s. So we see that if we write E as a function of the entropy and the other variables, then it has a minimum as a function of the other variables, which is reached at equilibrium. So it's reached exactly at the point where S had its maximum. And in general, we can see now that E is a convex function of S and of X. Now we turn to the important topic of the Legendre transformation, which plays an important role in thermodynamics. We do this in a mathematical way. We just have a general function f, which depends on two variables. Well, the xi can also be more variables, but let's stick to two, x and xi. And f is supposed to be a convex function of this x and of xi. And now let us suppose that somehow y is df dx. that y is a useful variable, in quotation marks. Variable or quantity. And what you can think of here is, for example, that F is going to be the entropy and X is going to be the energy, and we know that ds dE is 1 over T, and you will probably not deny that 1 over T, the temperature, is an important or useful variable or quantity. What we do now is we search for a function g, which depends not on x and xi, but it depends on y and xi, such that x can be found in a way from g, which is very similar to the way in which y was found from the function f. There is a minus sign here, so that distinguishes this expression from that one in the shape of the expression, but that's not very essential. The most important thing is that suppose that I have here a function s, for example, of the energy, and now I want to, instead of using the energy as a parameter, I want to use t as a parameter, and I want to extract the energy, and we want to keep the mathematical framework the same, so then it's useful to have such a function g from which I can extract the energy x in the same way as I did that in the previous case. Well, the solution to this problem is arrived at as follows. First of all, recall that we had y is equal to df, which was a function of x and xi dx. This gives us a relation between y, x and xi. And so from this relation we try to make x, the value of x, explicit as a function of y and xi. Whether that's possible, I will not go into that, but for a convex function that can always be done. We can write x as a function of y and xi. So I could naively now write g, y and xi as just f, and now I read x as being a function of y and xi, and then I have an additional xi. But it turns out that in order to satisfy this requirement, it's necessary to subtract here the x, which is a function of y and xi, times y. And so having this, we can show that indeed the d, g, dy gives me the required result. So let's do that. I need to take the derivative with respect to this y, so we have to use the chain rule. We first calculate df dx, and then we multiply that by dx dy. Then we move to this term. That gives me first the dx and dy, and that should be multiplied by y, which is still there. And then we have the derivative of y here with respect to y, which gives me just 1. So I get minus x. And now we note that because y is df dx, so this guy here is y, we see that the first two terms cancel, and we are indeed left with minus x, and that was precisely our requirement. We were looking for a function such that x could be extracted from that function as minus dg dy, and we have just shown that indeed this form of g satisfies that requirement. It's interesting to also consider the derivative with respect to psi. So let's have a look at dg d psi. That first gives me the explicit derivative of f with respect to psi, so df d psi partial derivative. But then of course there's also a psi dependence hidden in there, so we must add the df dx times dx d psi. And then there is a psi dependence over there. So we get again a minus dx d psi. And then we multiply that by y. Because g is a function of psi and y is now considered to be a constant. So that doesn't contribute itself to the derivative. Now we see that because again y is df dx, that the second two terms cancel. And we see, and that's quite a nice result, that the partial derivative of g with respect to psi is the same as the partial derivative of f with respect to psi. So if we are in equilibrium, and this would be thermodynamic functions, we would like this one to be 0, and we see that the same situation is reached in the g language, because then also the derivative is 0. For the sake of completeness, I also have written down here some properties which I do not prove in detail. But if f is a convex function of x and psi, and that we assume that at the outset, then g is a convex function of psi. And it turns out that it's concave as a function of y. So generally we have performed the Legendre transformation with respect to x, because we replaced x by y, and that turns convex into concave. The other variables, they are left, the dependence, the convexity or the concavity is left unchanged by the Legendre transformation. So now we perform such a Legendre transformation to the energy. Recall that we started off with the entropy as a function of energy and other parameters, and then we have inverted this function in order to turn it into a function energy, which depends on the entropy and the volume and the number of particles, and this was a convex function, which means that its second derivative is always positive. And we can perform a Legendre transformation, for example, with respect to the entropy. And that's what we are going to do now. So recall that the Legendre transformation worked as follows. We had f of x and psi. Y is df dx. And from that we found a Legendre transform, which was y as a function of g as a function of y and psi, and that is f x psi minus xy, where it is understood that x is to be read as a function of y and psi, which is this function is found from this condition. So let us now play that game for these. So E is my function f, and I'm going to find a Legendre transformation which I will call not G but capital F. So first of all we have S, V and N being the arguments of my function E. E corresponds to F, S corresponds to X, and the V and the N, they are examples of this variable psi. Then we have T, well here we have ds, dE, ds, because the x was s and f is e. And just as the s dE is 1 over t, therefore we have dE over the s is t. So we see that my variable y, that is nothing but the temperature. And we should read this as a partial derivative, so the n and the v are kept constant. What do we then obtain for the Legendre transformation, which is f, which now depends on y, so that's t, and the other variables, n and v, that's e, which depended on s, v, and n, but I will not repeat that here. And then we have minus x, that was s, and the y is the variable t. So we find that f is E minus Ts, and this f is called the Helmholtz free energy. Now recall that the energy as a function of S, V, and N is a very useful function. We had the first law, which says that dE is TdS minus PdV plus mu dN. And from this we can infer the following rules. dE ds at constant n and v is the temperature. We have that dE dV at constant S and N. That is the pressure. In fact, it's minus the pressure. And dE dN at constant S and V. That gives me mu. The question now is whether f is also a very useful function in the sense that we can derive all the useful other quantities from f. And it turns out that that is indeed the case. Let us look at df, which is, since f is E minus Ts, it should be dE minus dt times s. Well, we know what dE is, just written it up here. It's T ds minus P dV plus mu dN. And then I use the product rule for the second term, so it gives me minus T ds minus s dt. And we see that two terms cancel. And I'm left with df being P dV with a minus sign plus mu dN minus s dt. And so we have that df ds dt at constant n and v gives me minus the entropy. We find that df dV at constant n and t gives me minus the pressure, and df dN at constant t and v gives me the chemical potential. So we see that the structure is very similar to what we had seen for the energy. If I put it like this, it's nice and clear. You see here I have three rules which allow me to find the intensive quantities from the extensive ones. Here I have three different rules, and we see that now I have the derivative of f which itself is an extensive quantity with respect to an extensive quantity, so the result is intensive, and it's the same here. N is also extensive, scales with the system, so mu does not scale with the system. On the other hand, here I have the derivative of f with respect to an intensive variable, and therefore I get a extensive variable, which is the s. Let us now return to this Legendre transformation, where we derived the Helmholtz free energy from the energy. Now, if we are in equilibrium, then the energy reaches its minimum. So, for example, if the volume is free to change, it will change until the E is at its minimum. And now the question is, does the same hold for the F? And we can anticipate that that is indeed the case, based on what we proved before for a Legendre transformation, namely the dg dxi, so this would be the volume, this would be the Helmholtz free energy, is the same as the f dxi. So if this would then be the energy. So if this is 0, if the derivative vanishes, and it does so at the minimum, then also in the other case where we have the g, that's also 0, so that's also at a minimum or a maximum. And now it's interesting to give a physical example where we can see that this should indeed be the case. So here we have a volume which is divided up into two compartments, and there is a movable wall, and the movable wall can change the V1, but of course the V2 is always the V minus V1, and so that's not independent. And so V1 is the only independent parameter. And if we let such a system relax, we keep the total energy fixed. So we do not fix the temperature, but we fix the total energy. So we have E, V, and N as the variables. Then the volume will reach its equilibrium value that we indicate by a star. So this is the variable psi, because we are not going to perform the Legendre transformation with respect to the volume, but we do that with respect to the entropy, the S. So at that equilibrium, we will find a certain temperature. The temperature is found as dE ds at that equilibrium volume. And so we have an equilibrium situation where we know the energy, we have a temperature that we can measure, and we have a equilibrium for the V1, that's indicated by the star, and there is a entropy associated with the total system. Note that in this system we have fixed the total energy because we had an insulating wall. But once we have let the system reach equilibrium, then we can calculate the temperature inside the system. And now we can ask ourselves, what would happen if we make the walls no longer insulating, but they become conducting, and we put the system in an environment which has the same temperature as the system itself? Well, then we anticipate that nothing will change. So this is that new situation. We have now made the insulating wall conducting, and we have placed the system in an environment with the same temperature T as we reached before, after having the system come to equilibrium. And so of course nothing will change, and so we are still in equilibrium. And it's interesting that the Legendre transformation guarantees that if we now take the Legendre transformed and we take the derivative with respect to the V1, it will still be 0. And we can check that that is indeed the case. Let us write up the free energy. We omit the dependence on the number of particles because we don't change those. And the F will depend, of course, on the total volume and on the fraction that is occupied by the left compartment, which was V1. And, of course, there is a dependence now on the temperature T, because F does not depend on the entropy, it depends on the temperature. Now, the expression for F is E minus Ts, and we should keep in mind that in this case we interpret S as we view S as a function of E and V1. So we have S as a function of E and V1, and also here we consider it to be a function of E and V1. We keep V fixed, so we also omit the dependence on that V. Then we calculate the f dv1. First we will get an dE dv1, so that's the derivative with respect to this v1. Then we have a term where we use the chain rule. We take the derivative of E with respect to this S, and then we multiply by the derivative of S with respect to v1. And then we have minus t. T is one of the parameters, so if we take the partial derivative with respect to v1, it is considered to be a constant, and we multiply that by ds dv. But then we note that dE ds is nothing but t, and we see that these two terms cancel, and what we are left with is dE dv1, and that we calculate that at a constant s. And we have previously seen at equilibrium that this guy is 0, so also for f we find that it's at a minimum in equilibrium. Now let us recall quickly how we obtained the Helmholtz free energy. We took the energy as a function of S, V and N, and for reversible processes we can write the first law as dE is T ds minus P dV plus mu dN. So the E ds, the derivative of E with respect to S, is T, and we use that in order to perform the Legendre transformation with respect to S that we trade in for the new parameter T, and then we obtain the Helmholtz free energy, which is E minus Ts. This is an intensive variable, the temperature, and the V and the N are extensive because they scale with the system size. Then we can write the differential. dF is dE minus dTs, just like we did before. We get 5 terms, of which 2 cancel, and we are left with 3 terms. And from these 3 terms, we can easily calculate the partial derivative. So we can calculate dF dV, partial derivative. That gives me minus the pressure, which is an intensive variable. We can calculate dF dt, which gives me the extensive variable entropy with a minus sign, and dF dN gives me the intensive variable chemical potential. Now we go a step further. We start with f, which is a function of t, v and n, and now we perform a Legendre transformation with respect to its second argument, v. That means that we get a new function g, and that is written as f minus v times dF dv. That's just the prescription, the recipe for obtaining the Legendre transform. And as dF dv is minus p, we see that the second term here, v minus v times dF dv, can be written as plus p times v. And so, because f is E minus ds, we have E minus ds plus pv, and that's this new potential, which is G, and it's called the Gibbs free energy. If we calculate dG, then we find that dG is minus sdt plus vdp plus mu dN. It proceeds exactly along the same lines as we have used there. And from this I can, for example, see that dG dt is minus s, and we can find also that dG dp is v and dG dN is mu. It follows straightforwardly from this differential. We now can continue by taking Legendre transformations at will. We start again here from the Helmholtz free energy, F, and then we perform a Legendre transformation with respect to the particle number. In that case, we get a new potential which is called omega, and the name of that potential is grand potential. It's F minus dF dN times N. dF dN is mu, so we have F minus mu n. So we have E minus T minus mu n, and that's omega. I can calculate its differential, and we find this expression. So the omega dt is minus s, the omega dv is minus p, and the omega d mu is minus n. So that's new here because we have traded in n as a control variable by mu. What this describes is a system which is kept at a constant temperature, constant volume and constant chemical potential, but not a constant number of particles. So it's typically a vessel in which we put a system and then we punch a small hole in it so that particles can go in or out, and the final number of particles in that vessel is determined by the surroundings, and the surroundings, they have a certain chemical potential, and that controls the number, the chemical potential controls the number of particles in our system, in our vessel. Finally, we consider the Legendre transformation of the energy, not with respect to the entropy. So far we have first performed the Legendre transformation with respect to entropy in order to trade in the dependence on the entropy by a dependence on the temperature. We don't do that now, but we take the energy and immediately perform a Legendre transform with respect to the volume. And if we do that, we get a new quantity H, which carries the name enthalpy, and that's E minus the EdV times V. So that's E plus PV, because the EdV is minus P. And we find that the differential of this quantity is TdS plus VdP plus mu dN. So this is a system which is isolated from its environment and is closed off, for example, by a movable piston, so that the pressure inside the system is determined by the environment. Let us finally summarize the main points addressed in this movie. We work with thermodynamic variables, and they either scale with the system size, examples include the energy, the number of particles and the volume, or they do not. If they scale with the system size, we call them extensive. If they do not, we call them intensive. If we want to change the energy of a system, we can do that in two ways. We can either supply heat or extract heat from the system, or we can let the system do work, or we do work on the system. And the change in energy is then given by the heat minus the heat supplied to the system minus the work done by the system. For a closed system, we can define a quantity S, which is the entropy, and it depends on the extensive variables which characterize the system. And among those variables, there must be the energy, and then there may be additional variables. We call them here xj, but for a system like a gas or a liquid, you could think of the different numbers of the particle numbers of the different species of particles and the volume of the system. Now this S has certain properties. It should be extensive, so it should scale with the system size. It is convex, which means that it has this shape. And its derivative with respect to energy should always be positive, and we call that 1 over T, where T is a temperature. Furthermore, S has the tendency to increase, and it will increase until it reaches its maximum. For the S, we can formulate the second law of thermodynamics. The second law says that the change in heat the change in the entropy is related to the heat supplied to or extracted from a system in this way, where T times delta S should always be larger or equal than delta Q. If we have an equal sign, then we have a process which is called reversible, and if we have a larger than sign here, if it's strictly greater than delta Q, then it's a spontaneous process. If there's no heat supplied to the system and there's no heat extracted from the system, then the process is called adiabatic. And if the system is, during a change, always close to its equilibrium state, then we call it quasi-static. So all these qualifications here pertain to processes where we change something in the system. If a process is reversible, then it also should proceed very slowly, and that implies that the system is quasi-static, because a quasi-static process assumes that the system is always very close to equilibrium. A different way of formulating the second law is that heat flows always from a hot body to a cold body. And a Carnot engine, that's also due to the second law, it reaches its maximum efficiency when it's reversible, and the Carnot efficiency, which is then reached, is 1 minus Tc over Th. And if we have non-reversible, so we have also spontaneous processes, then the actual efficiency goes down. It's always lower than the Carnot efficiency. Then we move on to Legendre transformations. The general scheme is just a mathematical trick. We have a function f which depends on two quantities x and psi. We perform a Legendre transformation with respect to x, and we do that in order to move to a different parameter y, and that new variable is the derivative of f, the partial derivative of f with respect to x. That leads to a new function g of y and psi, which can be written in this form, where it is understood that x is to be read as a function of psi and y, obtained from this equality. And then we can find x from this function g as minus dg dy. So y is the f dx, then x is minus dg dy. So it's a nice symmetric structure. So let us see how these Legendre transformations play a role in thermodynamics. We start from the energy, which is a function of S, V and N, and we can perform a Legendre transformation with respect to the first argument, which is S. Well, we know that dE ds is 1 over t, and so we get a new function which now is called F. It's the Helmholtz free energy, and it's E minus Ts. If we calculate the differential, then we obtain minus S dt minus P dV plus mu dN. So from this we can find three partial derivatives from the Helmholtz free energy. Now we can take this Helmholtz free energy and then again apply a Legendre transformation in order to exchange dV for the P, for the pressure. So we can have a system in which we fix the volume, but we could also like to fix the pressure. And then we describe it by the Gibbs free energy, which is the Legendre transform of the F with respect to V, and it has the form of energy minus Ts plus PV. And if we calculate the differential, it has this form, minus S dt plus Vdp plus mu dN. Now we can also take the free energy and then perform a Legendre transformation with respect to the particle number n, and then we obtain the grand potential omega, which is E minus Ts minus mu n, and we can calculate its differential, and we see that we can obtain S, V and n as partial derivatives of omega with respect to t, p and mu respectively. Finally, we perform a Legendre transformation of the energy with respect to the volume, and then we find the enthalpy. The enthalpy is denoted by H, and the enthalpy is given as E plus PV, and here is its differential, and from it we see that we can obtain S, V and mu as partial derivatives of the enthalpy.